Think fast. What weighs more, 1 kilogram of feathers or 1 kilogram of iron? The answer is neither, because both are 1 kilogram, and that's kind of obvious. 1 kilogram is 1 kilogram regardless of the situation, right? Wrong! In this example, you are correct that the amount of mass in 1 kilogram of feathers is 1 kilogram, and that this is the same amount of mass in 1 kilogram of iron. You would also be right to think that if I put the kilogram of feathers and the kilogram of iron on a scale, it will be balanced. However, a kilogram is not always a kilogram. In the previous example, the amount of mass of iron and the weight it exerts on the scale are two different things. And I'm not just talking about the fact that scales measure the force weight of an object and not the amount of mass. I'm referring to one of the strangest facts in physics. A mystery so simple yet so profound that it defeated Newton and Einstein. Yes, a problem so difficult that the two greatest physicists in history simply gave up trying to solve it. This is the problem of inertia, and it explains why no one knows exactly what a kilogram is. And in fact, a kilogram is, at the same time, two things.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
To understand inertia, we need to understand what mass is. Mass is precisely the quantity that the kilogram represents, and the correct way to define mass is through Newton's second law. Newton's second law is the famous formula force equals mass times acceleration. Rearranging the formula to something more useful, the acceleration that a body undergoes is equal to the force exerted divided by the mass of the object. So, the more mass, the less acceleration for the same force. In other words, if a force causes an acceleration of 2 meters per second in an object of a certain mass, that same force will cause half the acceleration in an object with twice the mass. In this case, 1 meter per second, and this same force will cause double the acceleration in an object with half the weight, in this case, 4 meters per second. So, what we call mass is actually the property that a body has to resist changes in its motion due to a force. And knowing this, we can define a unit of mass as a kilogram. We just need to choose a reference object and see how it reacts to a known force. And then, we can call this reference a unit of mass and calculate the mass of other objects using the known force as a reference. If the same force causes more acceleration, the object is lighter than our reference. And if the same force causes less acceleration, the object is heavier than our reference. The problem is that it is difficult to create a force that can be precisely replicated. So much so that no one measures mass this way. Everyone uses a scale. But you and I need to have a serious conversation about scales. At first, what a scale measures is not mass, but the force of attraction with which the object we are measuring is pulled towards the ground. And in most situations, this is equal to the gravitational force on the objects. The gravitational force here on our planet is equal to the gravitational constant, the mass of the object times the mass of the Earth, divided by the radius of the Earth squared. It is possible to transform the terms of the Earth's mass, radius, and gravitational constant into a single constant, which is the gravitational acceleration constant on the Earth's surface, approximately 9.8 meters per second squared, which we will round to 10 for the rest of the video. With this simplification, the force of gravity is simply the mass of an object times the acceleration of gravity. This is the so-called weight force, mass times gravity. If an object weighs 1 kilogram, its weight force is 10 newtons. If it weighs 50 kilogram, the weight force is 500 newtons. When you place a scale under an object, the scale resists the weight force of the object, which is directly related to its mass. So, when the scale measures the weight force of the object, it can also determine the mass. Up to this point, everything seems normal, but it is not. And I will explain why. The force of gravity is closely related to the mass of the objects involved, but mass is the ability to resist movement. So, why is it that the ability to resist movement determines the force of gravity? For example, another force that behaves almost like gravity is the electric force. And the formula is exactly the same, just with different names. Electric force constant times the charge of one object times the charge of the other, divided by the distance squared. It is basically the same formula as gravity. The only major difference is that what determines the intensity of the force are the electric charges. The electric force has nothing to do with the mass of objects. Similarly, the force of gravity should depend on a gravity charge. A physical property that determines the attraction between bodies in the same way as electric charges. And for some reason, the gravitational charge is exactly the inertial mass as defined by Newton's law. The mass of gravitational force and the mass of resistance to motion are the same thing, and there is no good explanation as to why. If I told any physicist that the electric force depends on the mass of the object, they would think I was crazy. But the force of gravity depends on mass, and this is very, very strange, and no one knows how to explain why it is so. This is one of the forms of the problem of inertia. Why is the gravitational charge the inertial mass of objects? And now I ask you, what really is 1 kilogram? Is 1 kilogram the ability of a body to resist forces, or is 1 kilogram the gravitational load of a body? The answer is yes, to both things. But that is a very unsatisfactory answer, without the explanation of why they are the same thing. So, what do scientists mean when they refer to the kilogram? Well, they are referring to the official definition of the kilogram, based on reference measurements. We do not have a fundamental physical definition of the origin of mass that explains both inertia and gravity. But we have a world full of matter with mass around us, and we can use the material world itself as a reference. Until 2019, a kilogram was defined by a metallic cylinder made of a platinum-iridium alloy created in 1889, and this cylinder was known as the Big K. And it was literally what defined 1 kilogram. If you place this object on a scale and the scale showed 1.05 kilogram, it was your scale that was wrong by 0.05 kilogram, because the cylinder always had 1 kilogram. In fact, this metallic cylinder lost approximately 50 micrograms of mass between its creation in 1889 and 2019. This means that the very definition of the kilogram became slightly lighter over the last century. Yes, the very meaning of a kilogram varied with the reference, which is a problem. It may be that the pharmacy scale doesn't need this extreme precision, but cutting-edge experiments are starting to require a much more precise definition of mass. Much more precise than a block of matter can provide. And therefore, in 2019, a new definition of the kilogram was created, not using matter as a reference, but energy. A basically perfect sphere of silicon was created, and this sphere would be the basis for the new kilogram. The sphere was weighed against an extremely precise electromagnetic balance called kibble. The electrical energy required to balance the scale was measured with 15 decimal places of precision. Then, this measurement was used to create a definition of the kilogram based on fundamental constants of nature. Currently, 1 kilogram by definition is approximately 1.475 times the Planck constant of quantum physics times the oscillation frequency of the cesium atom, which defines the atomic second times 10 to the power of 40 divided by the speed of light squared. But no one is ever going to look at that formula and think, wow, look, a kilogram. This redefinition serves to ensure that the precision of mass measurements in experiments continues to increase. And who knows, maybe some future experiment will use this new precision in the definition of the kilogram to find evidence that helps with the problem of inertia. Because honestly, we need help, and Newton's story is a perfect example of that. The concept of inertia and mass is doubly tied to Isaac Newton. It is Newton's second law that defines mass as inertia, and it is his law of gravity that defines mass as gravitational charge. So how does Isaac Newton explain this coincidence? Well, he doesn't explain. Newton made it extremely clear that he did not know why his formula for gravity worked. He only knew that it did. So much so that Newton eventually invented answers just to stop them from asking. It was partly for this reason that he said the force of gravity is instantaneous. Not because he was sure it was, but because in practice it was. And they kept sending him letters about it. Newton was interested in another problem. Why is speed relative but acceleration is not? If you are standing on the sidewalk, the speed of a lamppost is 0 kilometers per hour, but for someone in a car, the lamppost moves at 40 kilometers per hour. The observed speed depends on the speed of the observer. Speed is a relative concept, but for both you and the car, the acceleration of the pole is 0. And the acceleration due to gravity is 10 meters per second, both inside and outside the car. Acceleration is not relative. Acceleration is absolute. Newton even provided an answer to this inconvenience, but this answer was more based on his religious preferences than on science. What is curious is that Newton's discomfort with speed and acceleration is also a form of the problem of inertia. To explain why acceleration is absolute while speed is relative, you will probably have to connect inertial and gravitational mass in the process. Or on the other hand, explaining the origin of inertia through gravity would solve Newton's problem of inertia. In fact, Newton came very close to this equivalence between these two problems. He devised a thought experiment that almost connects inertial mass and gravitational mass, stemming from his discomfort with relative speed. The experiment is as follows. Let's imagine that you have a bucket of water suspended by a rope, and then you spin the bucket. The water inside the bucket will start to spin in relation to the external world, and this movement of the water will cause it to take on a concave shape, like the whirlpool that forms in a glass when you stir it with a spoon. This is scenario 1. There is a relative motion of the water in relation to the rest of the world, and the water forms this whirlpool in the center. Now, let's imagine a second somewhat absurd scenario. Let's imagine that instead of spinning the bucket, we spin the rest of the universe around the bucket. Now, the relative motion between the water in the bucket and the rest of the world in this scenario is exactly the same. Would a whirlpool also appear in the bucket in this scenario? For Newton, it was obvious that it would not. That would be absurd. We didn't even touch the bucket. We just moved the entire universe. In other words, relative motion is not sufficient to explain the movement of bodies. We need some kind of true motion, which only happens in the first scenario. After all, rotating the universe is not going to magically make the water in the bucket start spinning. Or will it? Newton's bucket experiment didn't just occupy Newton's mind, but also Albert Einstein's mind centuries later. It reached the point where the problem of inertia was a great motivation for the young Einstein. It was precisely by trying to connect the origin of inertial and gravitational mass that Einstein began to work on general relativity, his own version of a theory of gravity. Einstein's dream was to create a theory of gravity in which gravity gives rise to inertia, that is, the existence of matter gives rise to space-time, and the resistance that massive bodies have to movement gives rise to inertia. In this theory, inertial mass and gravitational mass are the same by design and not by coincidence. In fact, in the ideal version of Einstein's theory, scenario 1 and scenario 2 of the bucket experiment are indeed identical. Spinning a bucket creates a whirlpool in the center of the bucket, and spinning the universe around the bucket while it remains still should also create the same whirlpool. In this theory, even the initial mass of objects is relative. So, moving something or moving the rest of the universe around, that something has to be equivalent, a complete equivalence that must hold for all forms of motion, both speed and acceleration. This is Einstein's ideal gravity, a completely relative world, where even mass is relative to the matter in the rest of the universe. Einstein's general relativity is not that theory. Einstein was unable to shape general relativity according to his philosophical ideas. In fact, he was forced to assume that inertial mass and gravitational mass were the same thing as a starting point. His dream was to explain this fact, but not even Albert Einstein succeeded, and this failure even affected his personal beliefs. He abandoned this project as he later came to disagree with it in his life. The truth is that to this day, no one knows what will happen to a bucket of water if we spin the universe around it. And to make matters worse, if we really want to know what a kilogram is, we will need to find out. So, do you like this type of video? What other topics would you like to see here on Scienceverse? Type your suggestions in the comments. And don't forget to like and comment on the topics that interested you the most. Thank you very much, and see you next time.